Okay, well, let's start the afternoon session. Our first speaker is Jan Rosseel, and he'll speak from Galilei to Euclidean, Carroll, and the Alice particle.
Yeah, thank you. Well, let me start by thanking the organizers for giving me the opportunity to talk. I will talk about from Galilei to Euclidean, Carroll, and the Alice particle, the times they are a-Changin. The title is slightly cryptic. The first part is word salads, and the second part is well, cryptic. The aim is basically the aim of the talk is essentially to kind of make you understand what Bob Dylan has to do with Carroll physics. So in particular that you are able to understand what the second part of the title actually means. So the talk will be based on work that was published on the archive last week in collaboration with Erik Bershoff, Luca Romano, Elena Simon Felix, and Sarah Zeko. And in essence, the main topic of this talk will be what I call generalized Galilean and Carrollian limits. They have already appeared this morning in the talk by Jelle. And in essence, what these limits are, they are limits in which, morally speaking, the speed of light goes to infinity or to zero in space-like directions. So if the speed of light goes to infinity or zero in all space-like directions, you're talking about Galilei symmetries or Carroll symmetries. By generalized, I will mean that the speed of light goes to infinity or zero, not necessarily in all space-like directions, but only in a subset thereof. That's roughly what you can understand with the term generalized Galilean and Carrollian limits. I will define more precisely how these are defined. What happens geometrically in such limits is that the non-degenerate Lorentzian metric structure of the relativistic theory that you start from degenerates, and typically you get two degenerate metrics or co-metrics. I will show you exactly what these look like. And let me just give you some motivation for why these limits are important. Well, Jelle already mentioned a couple of these things in his talk. One of the first instances where Galilean limits started reappearing in physics was actually in condensed matter physics. As Jelle explained this morning, Galilean limits and Galilean geometry are kind of the natural setting to formulate non-relativistic field theories on. They are the natural geometry on which non-relativistic field theories are defined. And similarly, Carrollian limits lead to Carrollian symmetries and Carrollian geometry that are the natural arena for ultra-relativistic or ultra-local field theories. So there has been a business in condensed matter to use geometry, non-relativistic geometry, to construct effective field theories for various strongly interacting systems, typically things like the fractional quantum Hall effect, where perturbative methods fail and you have to resort to writing down some effective field theory. And the idea is there that just like symmetries in effective field theory constrain the number of terms that you can write down, here you kind of use the geometrical structure of the theory to constrain the number of terms that you can write down in your effective field theory. Jelle also mentioned that in the stringy community, non-relativistic limits appeared in holography beyond ADS. In particular, Jelle was talking about Lifshitz holography and Schrödinger holography. There you are kind of trying to construct holographic duals for non-relativistic field theories, where the bulk spacetime is some sort of solution of general relativity plus some extra matter that is relativistic in the bulk. But as you approach the boundary, effectively what happens is that the light cone, the local light cone opens up so that effectively the speed of light goes to infinity as you approach the boundary. And then at the boundary, you end up with a non-relativistic causal structure that is described by non-relativistic geometry, Newton-Cartan geometry to be more precise. Similarly, in flat space holography, Carroll symmetry and Carroll geometry plays a role. In flat space holography, you take the boundary to be null infinity. Null infinity is a null manifold, and as Jelle explained, null manifolds are Carroll manifolds. As you approach a null manifold, the light cone completely collapses, and effectively the speed of light goes to zero. These are two instances where one uses ordinary Galilei symmetries and ordinary Carroll symmetries, so not really generalized. These generalized limits that will be the bulk of the talk, they play a prominent role in decoupling limits of string and M-theory and holography. And Jelle at the end of his talk was mentioning non-relativistic string theory as an example. That's an example where you take a limit of relativistic string theory. It's a target space limit. And effectively, what this limit means is that you take the speed of light to infinity in the target space-time directions that are transversal to a string broadsheet. So not in all space-like directions, but only in the target space, in the space-time directions that are transversal to the broadsheet of the string. What happens in this limit, you take the limit of a wound string, and what happens in this limit is that you only keep positive winding modes. The negative winding modes of the string, they become infinitely massive. So in that sense, it's a decoupling limit. And these decoupling limits, they lead to drastic simplifications in the theory. It turns out that the computation of scattering amplitudes becomes much simpler. And in this limit, the spectrum of the string is characterized by non-relativistic dispersion relations. So that's why it's called non-relativistic string theory. So in essence, what I will talk about is the kind of limits that lead to non-relativistic string theory, but even more general. This is a topic that is perhaps slightly out of the main scope of this conference. So let me just briefly say something about what the link of this topic with this conference is. Well, integrability, Andrea did a nice job this morning of bringing in the integrability aspect. You can, for instance, consider non-relativistic string theory, or you can consider non-relativistic limits of string theory on ADS5 x S5 and try to see what kind of, how you can attack the system using integrability methods, as Andrea mentioned. Concerning dualities, as Jelle mentioned, you can use non-Lorentzian limits as decoupling limits of holography. You can use non-Lorentzian limits to study holography around certain BPS sectors of the theory. And this will play a role in my talk towards the very end. It turns out that known dualities, in particular standard Maldacena-like limits that lead to standard holographic dualities, they can kind of also be reinterpreted in a non-Lorentzian way. And you will see what I mean by that towards the end of the talk. And finally, deformations. Well, you're dealing with contractions of Lorentz symmetry, of relativistic symmetries. These are typically non-semi-simple. There's a whole zoo of central extensions, non-central extensions that you can deform your algebras with. When you take these limits of things like string theory or brane actions, you get some sort of deformed string sigma models, deformed brane actions. There are also links with T-bar T deformations and so on. Okay. Yeah. So what I will do in this talk, I will first of all define what I mean by generalized Galilean and Carrollian limits, and I will revisit them in a way that unifies them. So typically, Galilean and Carrollian limits are treated differently. One is sending the speed of light to infinity in a particular generalized way. The other one is kind of the opposite thereof. You send c to 0. But it turns out that these two limits are actually much more closely related than one would think at first. And I will show you how that works. I will show you in particular that you can, there's one particular limit you can take, and depending on how you interpret it, it becomes Galilean or Carrollian. What's the advantage of that? Well, there has been a lot of work on Galilean limits in string theory, for instance. There are a lot of known results. And once you realize that Carrollian limits are very similar to Galilean limits, it allows you to translate a bunch of results that you know from Galilean physics to Carrollian physics. And I will give an illustration of that in the simplest example possible for the simplest limits that you can think of, namely just particle limits, Galilean and Carrollian limits of a particle. So what's the outline of my talk? I will first give you a review of generalized Galilean and Carrollian limits, as it is usually, as they are usually treated in the literature. Then I will discuss this unified way of treating generalized Galilean and Carrollian limits. I will show you that Carrollian limits are very closely related to Galilean limits, that you can, if you have a certain theory, you can typically take Galilean and Carrollian limits all at once. And I will give you one particular example. I will focus on one particular example, what I call the zero-brane Galilean and the Euclidean zero-brane Carroll limits. So the unification essentially implies that every Galilean type limits comes with a natural counterpart that is Carrollian. And so I will illustrate this for the ordinary Galilei limit that I call the zero-brane Galilei limit here, but it is the ordinary Galilei limit. And I will show you that there's a Carrollian counterpart that is the Euclidean zero-brane Carroll limit that is not the usual Carroll limit. So let me stress that from the beginning. This one here is not the usual Carroll limit. It's a very different thing. I will show you what these two limits physically mean. And then I will go through some consequences of the fact that these two limits exist. So as I said, you can use this machinery to kind of translate Galilean results to Carrollian ones. And in particular, here in this case, you know that if you take a Galilean limit of a relativistic particle action, you end up with a non-relativistic particle. I call that the Barman particle. There is now a Carrollian counterpart of this, and that leads to a different type of particle that we call the Alice particle. I will show you what this Alice particle is. It's a weird beast, so warning, it is quite weird. You will see how weird it is. Similarly, it is also known that the standard non-relativistic particle can be obtained from null reduction. And I will show you that that has a Carrollian analog. The Alice particle can also be obtained from null reduction. It's also kind of a weird null reduction. You will see in which sense it is weird. And then towards the end, I will convince you that these Barman and Alice particles are not completely academic, but they actually do have a role to play in string theory. The Barman particle can be viewed as a decoupling limit of a D0 brane. It is in fact the basis to construct the BFSS matrix model. The Alice particle has a similar interpretation. It is a decoupling limit of D0 star branes. These zero star branes are obtained by applying time-like U-duality, as was done by Hull at the end of the 90s. And so that kind of implies that the role that Galilean limits play in standard relativistic string theory has a Carrollian counterpart if you apply time-like U-duality. And then I will end with conclusions and outlook. So that's the rough outline of my talk, the summary in a nutshell. Okay, let me start by telling you what I mean by generalized Galilean and Carrollian limits. So if you think about the ordinary Galilei limits, it's a C to infinity limit that you take of special relativistic systems or in general relativity. And so C is a dimensionful parameter. So usually you don't want to take a dimensionful parameter to infinity. What you can do, however, is multiply C with a dimensionless parameter that I will call omega in this talk and send that to infinity. So what you do is, if you work in inertial coordinates x, you split them into the time-like one and the space-like ones. And the time-like one you multiply with this parameter omega, and then you plug this in everywhere, and then you send omega to infinity. If you do that for the Lorentz transformations, what happens is that particular terms drop out in this limit. In particular, the boost transformation of the time-like coordinate goes as 1 over omega squared and drops out. So you end up with a theory that features Galilei symmetries. So there's only like space-like rotations that act on the space-like coordinates, and then Galilean boosts that boost space to time. The time-like coordinates does not transform in the boost. And in fact, you have a notion of absolute time. I will define that to be absolute time, namely that the time-like coordinate does not transform in the boost. So every inertial observer agrees on the time interval between two events. So what happens is that in this limit is that the Lorentz group SO1, D minus 1 gets contracted to a semi-direct product of spatial rotations SOD minus 1 with boosts. The Carroll limit is similar. In this case, it's the C to 0 limit. Again, you implement it by multiplying C with a dimensionless parameter, in this case, 1 over omega. That's just because I want to send omega to infinity. I always want to, by convention, I always want to send my parameter to infinity, not to 0. And again, you can apply these limits to the Lorentz transformations. And what you find is that in this case, the time-like coordinate transforms under boosts to space, but the space-like coordinates don't transform under boosts. So that's the hallmark of Carroll symmetries. Time goes to space, but not vice versa. So in this case, it's space that becomes absolute in the sense that it does not transform under boosts. And the contraction of the Lorentz group, it leads to the same group. It's just that it acts differently. The boosts act differently. What I mean with a generalized limit is that to pass from Galilei to generalized Galilei, instead of saying that time becomes absolute, you're saying that a higher dimensional Lorentzian subspace becomes absolute. That's the quickest way of saying it. So it's now going to be a higher dimensional Lorentzian subspace that is boost invariant. And similarly for Carroll, instead of saying that space becomes absolute, it's going to be a lower dimensional Euclidean subspace that becomes absolute, that becomes boost invariant. How do you implement it? Well, essentially just by taking these rescalings and extending the index 0 to an index that I call alpha here, that contains time, but also a bunch of spatial directions. And then you just apply either the Galilei-like rescaling or the Carroll rescaling. This is how you implement, this is how these limits are usually treated in the literature. This is, however, not what I want to do. I want to show that you can do it in a slightly different way. That is much more unified. That's and in particular, what I want to do is I want to use a single type of rescaling. And essentially, what I want to do is I just want to pick this Galilean rescaling where you multiply a bunch of coordinates with omega and stick to that. And I want to see that you can also get Carroll by just implementing that rescaling. And you can. So let me just explain how that works. So I'm going to consider either theories in flat spacetime with inertial coordinates x as before, and the standard Lorentz transformation rule. You can also do it in curved spacetime. It's easiest to do this in terms of an orthonormal frame, a Vielbein, E mu A, with local Lorentz transformations. And the limit consists of 3 steps. In step 1, you split the index A, the coordinate index A or the flat index A in longitudinal indices and transversal indices. So you take p plus 1 longitudinal indices, I call them A prime, and d minus p minus 1 transversal indices, A twiddle. At this point, the splitting is completely arbitrary. The indices A prime, they can be whatever. The indices A twiddle, they can be whatever. In particular, time can be, it can be either longitudinal or transversal. Then you apply the Galilean rescaling that I've shown before. So you introduce dimensionless parameter omega, and the longitudinal indices you multiply, the longitudinal coordinates you multiply with omega. Same thing for the longitudinal components of the Vielbein, you multiply them with omega. And for the Lorentz transformation parameters, the purely longitudinal and purely transversal Lorentz transformation parameters, you just don't redefine them. And the mixed Lorentz transformation parameters that mix longitudinal and transversal, I will call that generalized boosts. Those you multiply with 1 over omega. You implement these redefinitions in whatever theory, whatever quantity you want to consider, an action, Lagrangian, symmetry transformation rules, whatever. And what I mean with the limit is sending omega to infinity in quotes. What I mean is that you just do an expansion of the quantity that you're considering in powers of omega to the minus 2, and you keep the leading order term in the expansion. That's by default what I define to be the limit. So compared to what I've shown before, the main difference here is step 1. The main difference is that I pick one type of rescaling, namely the Galilean one. And for the splitting in indices, I keep that completely arbitrary. I don't say where time is. So what you can do is you can plug these redefinitions in the Lorentz transformation rules and take the limits. Then you get these transformation rules. So you see that the longitudinal coordinates, they essentially rotate under the longitudinal part of the Lorentz transformations. The transversal coordinates rotate under the transversal part of the Lorentz transformations, but they also boost to the longitudinal coordinates. And same thing for the Vielbein components. And the thing is now that whether this limit is Galilean or Carrollian, that really depends on whether time is longitudinal or transversal. So at this point, I haven't specified where time is, and this choice, that's where you say that time is either longitudinal or transversal, that's the thing that is going to specify whether you're dealing with a Galilean or a Carrollian limit. So in particular, if you take time x0 to be longitudinal, then you are dealing with the Galilean limits. Simply because if you consider this boost transformation rule here, then you see that the transversal boosts to longitudinal. Time is one of the longitudinal coordinates. So you see that spatial coordinates, spatial transversal coordinates, they boost to time. That's a Galilean limit. We call that the p-brane Galilei limits. The simplest example is just p equals 0. That's the usual Galilei limits. In this case, you only have one longitudinal index, the time coordinates. The A-twiddle indices, that's all of space. And then this boost transformation rule here just reduces to the ordinary Galilei boost. If time is transversal, then you get a Carrollian limit. The reason is, again, because if you just inspect this boost transformation rule here, it sends transversal to longitudinal, but now time is one of the transversal indices. So in particular, the time coordinates will boost to spatial longitudinal coordinates. And that's a Carrollian type boost. We call this a Euclidean p-brane Carroll limit. The ordinary Carroll limit is an example of this. The claim is that these Euclidean p-brane Carroll limits, they contain all generalized Carroll limits that you can think of. The ordinary Carroll limit, the usual Carroll limit, is an example of this, and it's the case where p is equal to d minus 2. It's the case where we call it also a domain wall limit, simply because in that case, you only have one transversal index. And now the A prime, they are all Euclidean indices and they span all of space. So then this rule here just goes back to the usual Carroll boost. Yeah.
Excuse me, could you maybe say once more if you said it somehow? Why it's Euclidean Carroll limit and not just Carroll limit?
It's essentially because, yeah, so it's because we, when I do the splitting in terms of longitudinal and transversal, the name longitudinal and transversal I have in mind is that these are kind of limits that are associated to particular branes. So in particular, for the p-brane Galilei limit, you should think of these as limits. You consider a standard p-brane with a Lorentzian world volume, and you should see this p-brane Galilei limits as one where you send the speed of light to infinity in the directions transverse to the brane. In a similar way, in the Carrollian case, you're not dealing with ordinary branes with Lorentzian world volume, but the longitudinal indices, they are all Euclidean, so you're kind of viewing these things as limits that are kind of associated to Euclidean p-branes. That's why we use the word Euclidean.
Can I also you assume that time is in one of your on one side.
Yeah.
So if you do a split with null coordinates, that would give yet something else, or if you do a split with null coordinates and then put the omega to one side?
I have no idea what that would give. I will talk about no reductions and so on, but that's of course slightly different. So yeah, for the null coordinates, I'm not sure what you would get. So here I'm really assuming that you have standard time. So this slide basically explains the title partially. You can go from Galilei limits to Carrollian ones by changing the role of time. So Bob Dylan was truly a genius. He already knew this. So what happens geometrically is that the structure group, the Lorentz group, degenerates. So you take some sort of inner contraction of the Lorentz group in these limits. And in particular, what happens for the p-brane Galilei limit is that after taking the limit, you have a structure group that is a semi-direct product of boosts with a direct product of an SO1, p factor that acts on the longitudinal coordinates and an SOD minus p minus 1 factor that rotates the transversal coordinates. The standards, for this structure group, there is no invariant non-degenerate metric, but what you can construct is two degenerate metrics or co-metrics, I should say, more precisely. In particular, there's a Lorentzian metric of rank p plus 1. And there's also a Euclidean co-metric of rank d minus p minus 1. That's the metric structure that is compatible with this structure group. For the Euclidean p-brane Carroll limit, it's quite similar. Again, the structure group undergoes an inner contraction to a semi-direct product of boosts with a product of SOP plus 1 that acts on the Euclidean longitudinal coordinates, and an SO1, d minus p minus 2 factor that acts on the Lorentzian transversal coordinates. And again, this is compatible with a degenerate invariant metric structure, where now the rank p plus 1 metric is Euclidean, and the co-metric that is Lorentzian is of rank d minus p minus 1. And for people that know Galilean geometry, Newton-Cartan geometry, and Carrollian geometry, then you see that you get precisely the correct metric that is either metric or co-metric. Okay, so what I want to do now is, now that I've described these limits in full generality, I want to focus on one specific example, the simplest case where p is equal to 0. I want to first physically describe what these limits mean so that you get some more insights into what it is. And then I want to explore some consequences of these limits. So I'm going to consider the p equals 0 case, the zero-brane Galilei limit, and the Euclidean zero-brane Carroll limit. And as I've already said, the zero-brane Galilei limit, that is just a standard Galilei limit. So physically, what you do in that case is that you kind of, in this limit, you kind of focus on particular world lines that are inside this narrow red cone here. So these are basically world lines of particles whose speed is much smaller than the speed of light. So it's in this sense that this is a C to infinity limit. From the viewpoint of these particles moving inside this red cone, C is really very close to being infinite. It's very large. This kind of picture already suggests that this is a natural limit to take of particle actions. In particular, if you take the strict limits, then you're really focusing on a world line that just lies along the t-axis. That's a world line of a particle whose energy is completely given by the rest energy. That's a bit boring. In that case, you would just get like a particle that is just standing still. So this is not really what you want to do. What you want to do is really kind of take a slightly different limit in which you keep world lines of particles that you can view as small fluctuations around this static particle. So world lines whose energy of particles whose energy is dominated by the rest energy contribution, but not exactly given by the rest energy contribution. And that you can do by what is called the critical limits. Jelle explained it already this morning for strings. I will do it here for particles. So essentially what you can do is you can cancel the rest energy of the particle by adding a gauge field, by coupling the particle to a gauge field, and assigning a particular contribution to the t component of the gauge field that contributes to the energy to the Hamiltonian in such a way that it precisely cancels the rest energy of the particle. And then you're just left over with the fluctuations. This gives a standard non-relativistic particle. I will show you in a minute how you do this in practice, and it's called the Bargmann particle usually in the literature. Now, this Galilei limit, as I've just explained, it has a Carrollian counterpart. That's the Euclidean zero-brane Carroll limit, and I stress that this is not the ordinary Carroll limit, and now you can clearly see how different it is. Because essentially it's a limit that focuses on tachyons that move in a particular direction, so that have a speed in what I call here the y direction that is much larger than the speed of light c. So it's in this sense that the speed of light goes to 0 in one particular direction. It's simply because the particle is moving much faster than the speed of light in one particular direction. So from the viewpoint of these tachyons, the speed of light goes to 0 in the y direction. Just like in this case here, in the strict limits, you're focusing on a static particle whose energy is given by the rest energy. Here in the strict limit, you're focusing on a particle whose world line just lies along the y-axis and whose momentum in the y direction is just given by what you could call the rest momentum. Again, this is not what you want to do. That's kind of boring. You want to consider small fluctuations around this particular world line. So you kind of want to focus on world lines whose y momentum is dominated by the rest momentum contribution, but you want to kind of describe the small fluctuations. And again, you can do this in a critical by doing a critical limit. You can couple it to a gauge field that you tune in such a way that you cancel the rest momentum contribution. So that's physically what these two limits mean. So let's see how this works in practice for the particle. All right, here it is. So what I will do is I will start from the action of a relativistic particle that moves in a certain background metric that I call G. And it is coupled via a Wess-Zumino term to a gauge potential mu. And the metric I will, for convenience, write in terms of the Vielbein in order to take the limit. Note that I introduced a parameter epsilon here. That's a sign parameter. It's either -1 or +1. In case epsilon is -1, then there's a minus sign under the square root. The square root is then well defined for particle world lines of ordinary massive particles that move at speeds much smaller than the speed of light. So in other words, whose tangent vector is time-like. Such particles are sometimes called bradyons. This is the case, epsilon equal to -1. This is the case where we're going to take the zero-brane Galilei limits, the ordinary Galilei limits. If epsilon is equal to +1, then there's a plus sign under the square root. Then the square root is well defined for particles whose world line is space-like. In other words, tachyons. That's the case in which we're going to take the Euclidean zero-brane Carroll limits. Yeah, thanks. And in order to take the limit, what I do is I just split the flat index A into A prime, which I will now call S because it's a single index. And then the remaining indices I call A twiddle. For epsilon equal to -1, I declare S to be time-like because I want to take a Galilean limit. For epsilon equal to +1, I want to take a Euclidean zero-brane Carroll limit, so I declare S to be space-like. And the time direction will be part of the transversal directions A twiddle. Then you just apply the redefinitions of the Wheelbinder that I've already shown before. But in this case, you also have this extra gauge field, so you also have to give a field redefinition for that. You could just rescale the Wheelbind with, in this case, a convenient factor of 1 over the gauge field with a convenient factor of 1 over omega. But what would happen is that in that case, in the expansion of the action, the leading order contribution would come from the first term, the kinetic term. It would be of this form here. And if S is time-like, that's essentially a contribution from the rest energy. If S is space-like, it's kind of a rest momentum contribution. So that's not what you want to do. You want to cancel this. And in order to cancel this, you do two things. First of all, you take what's Jelle called, what is some sort of BPS-like limit, meaning that the coupling to the gauge fields, you declare it to be equal to the mass or related to the mass. And secondly, you add an extra contribution to the field redefinition from the gauge fields that is such that this extra contribution will precisely cancel this rest energy or rest momentum contribution. You do that, and then you end up with the following result. It's a bit abstract, but essentially what this is some sort of curved space generalization. In the epsilon equal to -1 case, the Galilei limits, this is a curved space generalization of a standard non-relativistic particle. It's, if you want, a generalization of the standard non-relativistic particle action written in arbitrary coordinate frames. And in particular, if you go to arbitrary coordinate frames, there's all kinds of fictitious forces that are contained in mu. And the time-like component of mu can also contain a Newton potential. If you want to see in the simplest case what this action describes, you just take the flat case in which you take mu equal to 0 and you consider an inertial coordinate system for epsilon equal to -1, where this flat metric h is just a Kronecker delta. You get a standard non-relativistic particle action, well known. Note that the constant that appears in front is m, the mass. If you take epsilon equal to +1, you're looking at the Carrollian limits. Then you get what we call the Alice particle action, and that's kind of a weird beast. First of all, the constant that appears now naturally has dimensions of momentum. It's kind of a remnant of the rest momentum, so it's more or less what you expect. But if you look at this action, the metric that appears here, that's an eta, so it's of indefinite signature. In other words, there's something ghost-like about this. There's one of the coordinates has the wrong sign of the kinetic terms. So this already kind of smells like ghosts. Let me just maybe briefly mention that in view of time, maybe. That's what I've done here in flat space. You can also generalize to include the cosmological constant. In particular, what you can do is you can start from the particle action in ADS or DS. You have to use particular coordinate frames, so you have to find the right sets of coordinates. That leads to a modification of this Bargmann and Alice particle, but you can do it. And the effect of the cosmological constant is actually contained in the addition of a quadratic potential that is multiplied by a constant k that is essentially a rescaling of the cosmological constants with a positive, it's a rescaling with a positive factor. So k is negative for ADS and it's positive for DS. So what you see here is that there's a sign difference. If you compare Bargmann and Alice, there's a sign difference when you look at the quadratic potential. And in particular, if you think about what's motion of the Bargmann particle, for which sign of the cosmological constants the motion of the Bargmann particle is stable, then it's for the negative sign of k, so in other words, for the ADS case. For the Alice case, it's the opposite. Alice particles undergo stable oscillatory motion for the de Sitter case. So Bargmann plays nicely with ADS. Alice plays very nicely with DS. That's the difference between the two. Okay. Okay, there's another property of the standard non-relativistic particle, that is that you can obtain it from null reduction. That's essentially because if you consider a null-killing vector, the little group has Galilean symmetries. So it's kind of natural that if you do the reduction over a null-killing vector, you end up with theory with Galilean symmetries. And if you do the dimensional reduction of a massless particle, you end up with a non-relativistic particle, that's the Bargmann particle. Since there's now a Carrollian counterpart of the standard non-relativistic limits, there should also be a null reduction that leads to this Alice particle. And that turns out to be true. Again, you can start from the action of a relativistic massless particle. You can do a null reduction. But in order to get the Alice particle, it turns out that you have to not start from a standard spacetime, but you have to start from a spacetime with 2 times. That's also contained in the title. It's the title of the song is not the time it is a-changing, it's the times they are a-changing. And in this way, the Alice particle is obtained from a reduction of a 2-time theory. So in particular, what you can do here is you can consider Kaluza-Klein ansatz. So null reductions, that's kind of that's usually treated as a bit of a fishy business. In the sense that if you do null reductions of quantum field theory and so on, there's various pathologies that are coming with it. Usually, in order to do that in a slightly more kosher way, you view null reductions as limits of either space-like reduction or a time-like reduction. And this is what I kind of illustrate here by writing down this metric. This metric you should view as a Kaluza-Klein ansatz. So in particular, this part here is a lower dimensional metric. Z is a compact coordinate. And then this part here is a contribution from a Kaluza-Klein vector. The epsilon parameter appears again, and then there's another parameter omega that appears again that I will take to infinity. So in writing down this ansatz, this is a standard Kaluza-Klein ansatz, but there is a particular tuning such that the omega squared term that you would get from expanding this term here cancels against the omega squared term here. So this metric ansatz has a well-defined omega to infinity limit. In case epsilon is equal to -1, where we want to take the Galilei limits, when omega is finite, then the compact direction is space-like, and the metric has signature 1, d. In case epsilon is equal to +1, the compact coordinate is time-like, and the metric has signature 2, d -1. There's a time direction hiding in here. Yeah, thanks. So what happens is that if you take the omega to infinity limits, z becomes null. What you can do is you can start from a massless particle action, moving in this background. You can restrict, it turns out that the z component of the momentum is conserved. You can restrict the particle action to the sector with constants pz, and you end up with either the Bargmann or the Alice particle action. And then at the very end, let me briefly tell you how this is related to string theory. So these Bargmann and Alice particles, they are decoupling limits, as I mentioned at the beginning, of D0 and D0 star branes. So in particular, here I am in ordinary string theory. If you consider M theory, ordinary M theory, and you consider superparticle excitations of the supergravity multiplets with non-vanishing momentum of the compact coordinates. So I'm assuming here I'm considering type 2a or M theory on a compact spatial circle. Then if you consider space-like reduction, you end up with 2a in 1,9 signature. And the superparticle gives you the D0 branes. And essentially what I've been doing here is take omega to infinity limits. The omega to infinity limits of the space-like reduction, that gives the null reduction. The omega to infinity limit of the D0 brane action, that gives the Bargmann particle. And what Hull did in the 90s, he was playing around with time-like T-duality. If you apply time-like T-duality, you end up in a very different world. It's truly a looking glass lens. You end up with string theories that have very weird properties. String theories where the natural branes are Euclidean branes. String theories where the natural vacua are de Sitter vacua. And that really smells like the Alice particle. The Alice particle is a limit of a Euclidean brane, it's a limit of a tachyon, and it's very compatible with de Sitter. So, and indeed, it turns out that in in Hull's time-like U-duality rules, there's an M-star theory in signature 2,9. You can start from a superparticle. You can compactify over the time direction. You can start from a superparticle with non-trivial momentum along the time-like direction. The time-like reduction gives a theory that is called 2A star in 1,9. The excitations of this superparticle or these superparticles, they give you what is called D0 star brains. And what I've done here in this talk is essentially just take omega 2 infinity limits. The omega 2 infinity limit of this time-like reduction, that's this null reduction procedure that led to the Alice particle. The omega 2 infinity limit of the D0 star brane, that's the Alice particle. And with this, I will just flash the conclusions and end in time. Thanks.
Thank you. Questions? Maybe I'll start with the question. So does it give you some kind of new type of holography for the BFSS matrix model, or is that?
No, yes. So it kind of there's an analog of the BFSS matrix model in this looking glass land of Hull. So in principle, if you start from the Alice particle, if you would consider multiple Alice particles, coinciding Alice particles, so multiple D0 star branes, and you would supersymmetrize it, then you would get a matrix model. You could call that BFSS star, and that should give you a non-perturbative definition or non-perturbative formulation of M star theory in 2,9. In the same way that the Bargmann particle, if you consider n coinciding Bargmann particles, you supersymmetrize, that is the BFSS matrix model.
And can you just remind the star in the BFSS, there would be a different signature in the star on the BFSS is a different signature in
exactly. Yeah. So I mean, by star theories, I mean any type of theory that is obtained via time-like U-duality. Those can be theories in different signatures, multiple times, even Euclidean signatures. There are some theories that also have standard signatures like 1,9. So like this 2A star is in 1,9. But it has ghosts. So what happens is that the Ramon fields, they become ghost-like in the 2A star theories.
I have two questions. You mentioned in one of your first transparencies that in the non-relativistic theories, you may have integrability. And I was wondering if you can have integrability in the non-relativistic sector without having it in the full theory. That's the first question.
Yeah, I think the natural experts to ask is Andrea. That should be the aim, right? That you really kind of construct theories that you can view as theories on their own.
Yes, but so these theories can have integrability without having integrability in the parent theory before the limit.
It's a question to understand if integrability of the parental theory supplies the limit. So
yeah, but I'm asking the opposite. Can you have integrability after the limit is taken without having it in the first place? This is similar to saying that, for instance, the BMN limit of n equal 1, you can have, it's in common with n equal 4, the BNM limit of n equal 4, but before the limit, they're completely different theories.
yeah.
Anyway, that was my first question. And the second is, in mathematics, besides the contraction, there is also what is called expansion.
Yeah.
Which means you can build the, let's say, the SO3 out of the Euclidean group in 2 dimensions. Can you see some of it in this business, or that's a general question?
Yeah, so this is not what I did. I did strict limits. And these are in these strict limits. What happens is that the structure group undergoes an intermediate contraction. You can also do more in the spirit of what Jelle was explaining this morning. You can also consider expansions. So 1 over c squared expansions. There, the natural symmetry algebras are precisely given by Lie algebra expansions. So in some sense, there you start from Okay. Yeah.
So what I've known so far is that Carrollian physics can also be obtained at the null hypersurface in a Lorentzian spacetime, while the Galilean is obtained as a null reduction.
Yeah, this is
And
different.
here you obtain both as null reductions, but for different
Yeah.
geometric signatures. So could you also somehow obtain the Galilean physics in something like the null?
Yeah, it is suggestive
Yeah,
in the sense that, so you're right, standard Carroll. So what the null reduction that is described here, this is for this Euclidean zero brane Carroll limits. That's, as I explained, that's not the standard Carroll. But standard Carroll can be obtained by, I wouldn't call it a dimensional reduction, but it's some sort of restriction to a null hypersurface. It's quite a different procedure from what I explained here. This is a standard Kaluza-Klein reduction. The unification of Carrollian limits and Galilean limits should imply that if you can obtain Carrollian theories from restriction to a null hypersurface, there should be something similar for the Galilean counterparts of the. And in this case, that would be the d-2 brane Galilei limits. That's the Galilean counterpart of the standard Carroll limits. But it is indeed suggestive that that should be the case. Yeah.
Okay, very quick last.
So, do you think there is through the looking glass, when you go to the type 2 star, there is a kind of Gomis-Oguri non-relativistic string?
Yes.
So you have this big field that can cancel
everything. There is, yeah, we're working on that. That's work in progress.
Okay.
Okay, we'll have to move on.